So good morning.
Yes, sir. Good morning.
Good morning, sir.
Last class we have seen Q point, okay, DC operating point or DC quotient point, or in short it is called Q point. Now we have assumed that this Q point should be fixed, even though we are changing the different voltages and currents in the circuit. Okay, but actually this Q point gets shifted due to several reasons. What are the different factors which affect this Q point? Okay. Ideally, this Q point should be fixed, and we have to ensure that these Q points should not get drifted. Okay. Now we will find out what are the different reasons for which this Q point gets shifted, and then we'll design the circuit accordingly, which will ensure or which will lead to the circuit which will be independent of The screen is still visible. Suddenly it got switched off.
Yes, sir.
Okay.
Yes, sir.
First external parameters which affect this Q point is inherent variation of transistor parameter. Like we have seen beta IB plus, we have already derived this 1 plus beta into ICO. Okay. So this equation contains three variables. One is beta, one is IB, one is ICO. But all these three variables are found to be strongly dependent upon temperature. If the temperature increases, these variables also increases. This will result in the increase of collector current. And the moment IC is increased, definitely the Q point will be shifted. Q point is shifted, which is not required. We want this Q point should be fixed at a particular point. At a particular point means for a particular value of IC and the corresponding VCE. This X and Y coordinate, this will define the Q point. Okay. I repeat, beta, IB and ICO. Please switch off your mic. Where switched it on? Ankita Ghosh. Switch off your mic. Okay, so somehow we have to design the circuit which will ensure that this will be independent of beta, it will be independent of IB and ICO. This is the first factor which affects the Q point shift. The second is variation in parameter of transistors of the same type. You take two transistors of same model, same make, same fabrication technology has been adopted, but you will find the value of the internal parameters are different. Like beta will not be same. Okay, in one case, let's say beta is 100, second case it will be 101, and so and so. So there will be little variation in the beta value, even though you follow the same steps to fabricate the same type of transistor. Okay, you won't get the same level of beta of same type of transistors. Okay, so these are the main reasons why Q point gets shifted. And the performance will be defined by a metric called stability factor. There are three types of stability factors. One is S, then we'll discuss S dash, then we'll discuss S double dash. First stability factor S. This stability factor is defined as the rate of change of collector current with respect to change in the leakage current. I repeat, the stability factor is defined as the rate of change of collector current with respect to the reverse saturation current, keeping the common emitter current gain beta and the base current as constant. Okay, this is very important. If you change the value of beta, because there are three parameters, one is beta, one is IB, one is ICO. Okay, so what we will do, we will find out the contribution of ICO, which is nothing but S. We will find out the contribution of IB, then we will find out the contribution of the beta, beta. Okay, and together these three will change the Q point. Okay, so individually we will find out, we will define the stability factor, and then in practice we will find that all three gets varied, and then the total change in collector current or VCE will be due to the individual change in ICO, IB and beta. Okay. Now what will be the lowest value of this stability factor, or the system will be stable? What could be the value of S? Because see, if you change ICO, same level of IC will be increased. Okay. On the worst case, you will find you double this ICO, IC is getting 4 times. So that will be even worse. Now worst case is, or should I say the best case is, if you increase ICO by 2 times, IC will be increased by 2 times. So the lowest value of S will be equal to 1. And that should be our target. We will design the circuit in such a way that the stability factor comes out to be equal to 1. Now let us calculate the stability factor. Let's say IC is beta IB. This is the equation we have already derived. Now if we differentiate it with respect to IC, so this will be 1, this will be, take beta, right? Beta is constant, we have assumed. See, the definition of stability factor says that beta and IB will be taken as constant. So here also 1 plus beta will be taken as constant. This is ICO by IC. So this is beta DIB DIC.
Sir, it is ICEO or ICBO? ICO. What is?
We have already discussed it. Check the earlier lecture. Okay, what does this ICO means? We have already clarified that point. And this is, by definition, this will be 1 by S. So if you just simplify, this will be 1 plus beta divided by 1 minus beta DIB DIC. Okay, change in base current with respect to collector current. This will be the generic formulation for stability factor for a given circuit. So for any given circuit, we will find out the relation between IC and IB. Then you just substitute DIB DIC here. That will be the value of stability factor with respect to IC. That means change, with respect to ICO. Change in IC divided by change in ICO. Okay. Now, we will apply this concept in common base circuit. We will see what will be the stability for common base circuit. What is the relation for current, different current levels, alpha IE, ICO. If you take the derivative of this is with respect to ICO. This is 1. Okay. So the stability factor for common base circuit is equal to 1, and which is the lowest possible stability factor for any given circuit, and that should be our target. We should make the stability factor should be equal to 1. And from this respect, common base circuit is the best circuit out of 3 different configurations. In one class I was telling that don't assume that common emitter configuration is the only circuit which is being used. If the stability criteria is the only criteria to determine the performance, then common base will be the choice. Okay. For common emitter, we'll write down the same equation, 1 plus beta ICO. Okay, so this is for common emitter. We are going to derive the stability factor for common emitter circuit. And again, if I take derivative with respect to ICO, this is 0. Why 0? Because we have assumed beta and IB, these two are constant. This is equal to 1 plus beta. So the stability factor for common emitter is 1 plus beta. That means if beta is, let's say, 100, so S value will be equal to 101. What does it mean? That means if ICO is increased by 1 times, then IC will be increased by 101 times. So change in IC will be 101 times more compared to the change in the leakage current or reverse saturation current or ICO.
Sir, please, sir, please show the previous slide, sir, again.
Common base circuit.
No,
Or previous, sir.
thank you, sir. Okay.
Again previous.
No, sir.
This one, this is the generic equation for stability factor. So for any given circuit, I am just giving 2-3 simple configurations, but for any given circuit, you have to carry out the stability factor. And the lower the stability factor value, the better will be the circuit configuration. Okay. So you can conclude that common emitter circuit, the collector current is highly dependent upon the reverse saturation current. Okay. And it depends upon reverse saturation current means the performance will be dependent on the temperature as well. And to avoid this, because our target, I told, our target is to reduce this 1 plus beta to 1. For that you need a certain circuit arrangement which is called efficient biasing or proper biasing. Okay. Proper biasing means you connect external resistances and voltages accordingly so that the final stability factor expression will be approaching to 1. What are the different conditions for which proper biasing? First one is you have to select proper DC value of collector current. Then proper value of VBE. This VBE will give rise to the value of IB. Okay, and normally this is 0.7 volt for silicon and approximately 0.3 volt for germanium. And you have to select a proper value of VCE. These are the 3 parameters which will guide you whether the biasing has been accomplished or not. You have to select a proper value of IC, okay, VBE, which is nothing but IB, and VCE is the collector to emitter voltage. These first 2 conditions is to make sure that base to emitter junction is forward biased and base to emitter junction will be forward biased during all parts of the signal. This third condition is to make sure that collector to base junction is reverse bias. Reversed bias. Okay, if you select IC and VBE in a particular value, then the base to emitter junction will be ensured to be forward biased. Collector to base junction will be reverse biased by looking at VCE. Now there are different nomenclatures given for the circuit elements, different circuit elements. We can write down methods of transistor bias. Different bias elements will have different values of S, that is stability factor. And the base circuit element will be which will lead to S value nearly equal to 1. First circuit is base bias, or it is known as fixed bias. I'll tell you why it's called fixed. Then base bias with emitter feedback. Or sometimes it is called emitter bias. Third one is base bias with collector feedback. Collector. Switch off your mic. Should I tell your name and then only you will switch on? I can see here. Fourth one is voltage divider bias. Okay, so we'll quickly go through the circuit arrangement and we'll find out the value of stability factor for each configuration, and then you can make a comment whether out of these four different actually there are many such configurations, but four are there in your syllabus. Out of these four configurations, which one will be the best choice from the stability point of view? Base bias or fixed bias? Okay. Now, one question could be that why always we write common emitter configuration in the circuit. The reason is common base configuration, there is no bias arrangement required. There is no external biasing required because the value of stability factor is equal to 1, even if you don't go use any biasing. Biasing is important for common emitter configuration because the value we have calculated already, it was 1 plus beta. So our target is to reduce that 1 plus beta as much as possible. Okay. This will be the base bias arrangement. Okay. If you take this input loop, this is IB into RB. So this will be IB, this will be IC, and purposefully I have assumed that there is no emitter resistor, otherwise calculation will be a bit difficult. Okay. At your higher semester, those who will study this electronics, they will include this emitter resistor later. Okay, so if you take this input loop, looks like this: minus VBE plus VBE minus DVB equal to 0. So from here I can calculate the value of IB. IB is VBB minus VE by RB. Let us mark equation number 1. Now if you look at this right hand side of equation 1, VBB is constant, VBE is also constant, RB is also constant. Okay, so definitely IB also will be constant or fixed, and that is the reason why it is called fixed bias. Okay, because the base current is fixed or constant, it is known as fixed bias. If you now if we take this output loop, Okay, different voltage drop in a particular loop will be equal to sum up to be 0. Okay, that's the rule of Kirchhoff's voltage law. So here you can calculate VCE is nothing but VCC minus IC into RC. Let us say equation number 2. And what is IC? IC is equal to beta IB. And now what is the stability factor for this base bias circuit? Umang, you are been noted, huh? So for this base bias, the stability factor, because this is only because there is no emitter resistor, it is as good as common emitter configuration. So stability factor S for this case also it will be 1 plus beta. So you won't get any improvement in the stability factor. It was as good as 1 plus beta, and which is the worst possible stability factor you can get out of common emitter configuration.
Sir, why 1 plus beta?
We have already derived, for common emitter it is 1 plus beta.
Yes, sir.
For common
Yes, sir.
emitter, because there is no modification apart, because see this emitter resistor we have not included. Okay, the other things here you can find out. You just substitute IC, beta IB and ICVO. Okay, 1 plus beta into IC. We will take this derivative. The way we have done for simple common emitter configurations. Okay. Here
Okay,
I have
sir.
told how to calculate the different values of IB and why it is called fixed bias, because this IB is constant. Once you know IB, you can calculate IC to find out the Q point. Once you know IB, you have to calculate VCE, and these 2 points will give you the operating point for this particular circuit. Okay. The second circuit will be emitter bias, or sometimes called base bias with emitter feedback. That means there will be a feedback circuit. This is RC connected to VCC. Here you will find RE is included. This is VBE. Okay, again you have to take in a very similar way, you have to take input loop, output loop. You have to find out the value of IB. Once you know IB, you can calculate IC. Once you know IC, take the output loop to find out the value of once you know IB, take the output loop, you can calculate the value of IC. And IC and VCE together will give you the DC operating point. Now, regarding the stability, for this particular circuit, I will, you can write here. Okay, if you take this input voltage loop, I will write here itself. VBE plus, okay, there is current flowing through this RE is IE. So IE RE minus VCE IBRB. This is equal to 0. So if we simplify, okay, where you assume that IE is equal to 1 plus beta into IB. You just substitute because I need in terms of the constant parameters. So the IB will be calculated as VCC minus VBE divided by RB plus beta plus 1 into RE. Now once you know IB, you can calculate IC. This is beta IB. That is beta into this particular equation. Okay. This will give you the value of IC. Now to find out the value of VCE, you take the output loop. Output loop means this particular part. VCC will be there, ICRC will be there, VCE will be there, and IE into RE. So all together will be equal to 0. So VCE, IE, RE plus these are the potential drop across RC and RE equal to VCC. So if I put it in a y equal to mx plus c form, this will be minus IC. Let us say equation number 2. Okay. See the variation, VCE will be there in y-axis, IC will be there in VCE will be in x-axis, IC will be there in y-axis, and you can plot it. Find out the value of VCE because we have already calculated the value of IC from first equation. Now what will be the stability factor? For stability factor, I'll write down this equation again because I'm finding the stability factor with respect to ICO. Okay. Now to find out IC, I need the value of IB, and we have already calculated from this equation. Okay. So to find out the stability,
Previous slide, sir.
this one.
Sir, IE RE plus IC RC, the minus IC common.
Huh?
Sir, yeah, IE will not be.
UC
IE will be
minus
not.
IE RD minus RC RC, sir.
IERE.
Yes, sir. IC RC.
You have replaced IC with IE with IC.
Oh, okay, I understand. So you, or else here you can write down 1 plus, what is this? Beta into IC, right? So
Yes, sir.
now you find out IC is a common factor. You simplify this. This equation will be okay. This equation will be okay. Just substitute the value of IC, beta, I, RE, IC, RC, and VCC, and find out the value of VCE from here, right? Okay. What I have done, I have just approximated, assuming that IB is negligible, just to make the equation simpler, or else you can always substitute 1 plus beta into IC. Okay. Stability factor is important for me. Stability factor, so I'll again write down this input loop. IB, RB is equal to 0. Again, IE is equal to IB plus. Okay, so I'll not assume any negligible parameters. So include this IB into account. Okay. To find out the value of IB, this is VCC. You just substitute IE equal to IB plus IC, and then take IB to one side. This is VBE minus this divided by RC, RE plus RB. Okay. This, let us say, equation number 1. Okay. Now if you take this derivative of IB with respect to IC, what will be the value? Because this is VCC is constant, VBE is constant. Okay. And if you are taking with respect to IC, that means this will be minus RE, right? So this will be minus RE divided by RE plus RB. Okay, let us equation number 2. And we have already derived the generic equation for stability factor, that is 1 plus beta divided by 1 minus beta diV dic. And we have calculated for this circuit, we have calculated diV dic value comes out to be minus RE divided by RE plus RB. So you substitute here, this will be 1 minus beta. This is minus RE divided by RE plus RB. And if you simplify this RE plus RB, this minus minus plus 1 plus beta divided by 1 plus beta into RE divided by RE plus RB. This will be the stability factor for the circuit called emitter bias. And you choose this value. Now why I am telling how to make this circuit independent of this variation. See, if I manage to have RE is approximately equal to, okay, it will never be possible. If I make this, then definitely this particular component will be equal to 1. So the overall component will be 1 plus beta divided by 1 plus beta, that comes out to be 1. You understand? If I assume this RE is approximately equal to RE plus RB, that means RB is as low as possible. That means this ratio RE divided by this will be equal to 1. Overall component value will be 1 plus beta divided by 1 plus beta. That comes out to be 1, and which is the lowest possible value of stability factor you can achieve out of it. That is what the design is all about. That what will be the value of RE? Somebody can ask that why the value of base resistance will be less for this particular circuit. Okay, so these are the typical questions been asked from technical side. Next circuit is collector feedback bias. Collector feedback bias means there will be resistance connected from the collector to the base circuit. Looks like this. This is RC. Remember, this is the collector terminal. So there will be a feedback from this collector to base. Okay, so this is base terminal, and this is the emitter terminal connected to VCC. Okay, different currents, voltages. This will be VBE. This will be VCE. Now the collector current is actually the current which is flowing through the collector terminal. Okay, so the total current flowing through this RC will be something different. So this is, let's say, IB. Let us say this is IB. That means same current is flowing here. That means total current flowing through this RC will be equal to IB plus IC. That's the total current getting divided into two components. One is feedback circuit passing through RB, and the current flowing through RB is, this is RB, is IB, and the collector current is IC. Okay. Now take this output loop. You take this input loop, because input loop will give you IB value, output loop will give you VCE value. Okay, directly I have written IB plus IC. IB RB. So if I simplify, the value of IB will be VCC minus VBE, this by RB and once you know IB, IC can be found out by beta IB. Now to find out VCE, you have to take the output loop. Output loop will have VCC, then RC, then VCE, and there is no resistor from the emitter terminal. So IE will be equal to 0. So output loop, if I write, this is VCE minus VCC plus ICIB into RC. From here you can find out the value of VCE. For stability factor, again you have to go to the input loop. The same equation which we have written, VBE minus VCC, this equation. Okay, equation number 1. And we have already calculated IB. Because I have to find out the value of IB and then I will take DIB DIC. Once you know DIB DIC, then substitute this particular component in the stability factor expression, you will get the final stability factor. This is VBE now if I take derivative with respect to IC, okay, that means this is constant, so this will be 0, this is also constant. We are taking derivative with respect to IC, so this comes out to be RC divided by RC plus RB. And you substitute this in the stability factor expression. There in the last circuit it was RE, here it is RC divided by RC plus RB. Stability factor expression is 1 plus beta divided by 1 minus beta DIB DIC. Right, DIB DIC you have already calculated, minus RC divided by RC plus RB. So minus plus, this is RC divided by RC plus RB. In a very similar way, you can also design the circuit so as to make sure that stability factor value should be reduced. Stability factor lowest value should be equal to 1 or else it will be approaching to 1. The best stable, or should I say the stable circuit, indicates that the stability factor value S will be equal to 1 or nearly equal to 1. Okay. The last bias circuit is very popular in the sense that it is most stable, in the sense it is again equal to, you will find it is approaching to S equal to 1. Okay. That is known as voltage divider bias or potential divider bias. Definitely circuit will be a bit complex compared to the earlier 3 circuits. RC, RE, there is a potential divider at the base terminal. We assume R1 and R2 are the 2 different voltage levels, and the voltage is connected, because we are connecting collector terminal to a power supply, we give VCC, but remember it's a DC power supply which will guide you the value of IC and VCE. So this is collector current, this is base to emitter, this is IE, and this is VCE. You know how to find out the value of voltage at this point, VB. Okay, it's a potential divider bias. 2 resistances are in parallel, and the voltage across this R2 will be considered as VB, because VB is the voltage at this point with respect to ground. So I assume this particular terminal is grounded. Okay, so this voltage will be R2 divided by R1 plus R2 into VCC. And if I take this input loop, this is VBE plus IE RE, this is equal to VB. Okay. IE RE is the potential drop across E, and if I substitute IE is equal to beta plus 1 into IB, so we get VB minus VBE. Because our target is to find out the value of IV. Okay. So this will be VV minus VBE divided by beta plus 1 into RE. RE. Now once you know IV, from IV you can calculate IC. Okay. IC is beta IV. And we take this output KVL, output voltage loop, BCC, ICRC, BCE and IER. All together, if you use this polarity concept, then the summation will be equal to 0. BCE, IER. Because see, we have already calculated the value of IC from IV. Okay, once you know IC and IV, you can calculate IE. IC known, RC is known, BCE is to be found out, BCC is known, so this is what you have to find out. IE is known and RE is known.
Sir, can you show the previous slide? Yes, sir. Done, sir.
Sir, why are R2 by R1 plus R2?
This is class, should I say class 10 concept, not even class 2. The voltage at this point, where R1 and R2 are in parallel, okay, the voltage developed across R2 will be equal to the effective resistance multiplied by actually the total voltage. You find out what is the current flowing through this. What will be the effective resistance? Two parallel resistances. What is the effective resistance of two parallel resistances? Or equivalent resistance. That's the terminology you have gone through. You brush up your class 10 knowledge. Okay. I cannot start teaching that this is the parallel combination of resistance, series combination of resistance. Huh? If you have forgotten, I suggest that you go through those books which you used to study. The final stability factor, actually, I can derive this equation, but then you need a concept of Thevenin equivalent. You know this?
Yes, sir.
Yes, sir, we know that.
Yes, sir.
Yes, sir.
Yes, sir.
Normally, from the design point of view, I can tell you the value of R2, normally will be equal to 0.1 beta RE. The choice of R2 will be in such a way that it will be less than equal to 0.1. There is a specific reason. Okay. I'm not getting into those details, but you remember this condition that it should be equal to 0.1 into beta RE. And the stability factor for this particular circuit, voltage divider by circuit, this is the stability factor expression for potential divider or voltage divider bias. Actually, it depends on alpha, R1, R2 and RE. Okay, R1, R2 and RE. But in the circuit, you will find there is a RC present in the circuit, right? Truly speaking, the stability factor does not depend on this RC. Okay, it's only the R1, it's only R2 and RE which will determine the value of the stability factor. Over and above, the value of R2 is chosen in such a way that it is less than equal to 0.1 beta R. Okay. This is the stability factor, or should I say the change in variation of IC with respect to the leakage current. Now there are two more parameters which affect the performance of the circuit. One is the second one is called bit IB. Third one is beta, right? There is one more stability factor called S dash. This is defined as change in the collector current with respect to beta IB. Sorry, change in collector current with respect to change in IB. This is one more stability factor. You have to consider all these three contributions together to find out the total variation of collector current due to individual three components. Another stability factor which is defined as S double dash, this is defined as change in collector current with respect. Now remember, whenever I am assuming that change in collector current with respect to IB, I have assumed that beta is constant and ICO. This because there are three parameters, two have to be made constant, the other is variable. Here it is beta and ICO and IB are constant. So individually you calculate these three contribution of change onto IC, and then the final output will be change in collector current will be S into change in ICO, because S is defined with respect to ICO. S dash is defined with respect to IB, and IB is actually a direct function of VBE, and we have already discussed how you can calculate IB. The third contribution is due to beta. So change in beta multiplied by S dash, change in IB or VBE multiplied by S dash, and change in collector leakage current multiplied with S. These together will give you the total change of collector current. And at the end I can say this collector current change should be lowest possible. To ensure that DC operating point, and DC operating point I have been referring to these two parameters IC and VCE, to ensure that this DC operating point should be fixed. Fixed means it should not move. It should not move on y-axis or x-axis. Okay, so the value of IC should be kept constant. VCE should be kept constant. Okay, and once IC is changing, once IC is changing, VCE also will be changed, because we have seen the output current equation, output voltage law. There VCE was a function of IC. Yes.
Sir, S dash should be multiplied with delta IB now.
That's what I have told. Delta IB and VBE, even though one is current, one is voltage, right? You can write delta IB, but delta IB will be generated. Delta IB cannot be controlled. What you can control, or what you can see in the circuit is VBE, right? You ensure that VBE is going to be fixed. The moment VBE is fixed, like this. See, VB is the potential that we are going to find out. Okay, voltage. So what you have to ensure that this particular VBE parameter, you make this as constant. This is to be fixed, and then only IB will be constant. Okay, so even though one is current, one is voltage, I can interchangeably use that. Either it is change in VBE, which directly affects the value of IB. Okay, here you find out the lesser the VBE, definitely the base current will be increased. Base current is increasing means collector current is increasing. That means your operating point is shifted. So to stop this shifting of IC, I have to ensure that VBE should be kept as constant as possible. Okay, nearly it should not. The change should be nearly 0. Any other queries?
So what is the value of IC in this equation? So can you show the previous slide? The previous one.
This one?
Yes, sir. Yes, sir.
Oh, this one. Now for voltage divider bias, I can write down this emitter current. This will be Thevenin equivalent minus VB divided by RE. Okay. Here also you will find that this is a direct function of VBE. So VB is very, very important, and even though we say it's a voltage, but this voltage actually gets drifted, okay, due to other reasons also, okay, because the total device itself is a nonlinear characteristics. Even though we map Ohm's law inside this semiconductor device, but truly speaking, not even a single region where this Ohm's law is applicable. Okay. But for doing the calculation in a simpler manner, we assume that some part is following the linear characteristics. Okay, so any other queries?
Sir, in this configuration, the resistances do fall in the linear region, right?
Resistances
The resistances do fall, means do follow the Ohm's law, right?
X. Resistances follow the Ohm's law. Didn't get.
Sir, you said that nothing,
Circuit I am talking, huh?
nothing here follows that linearity, so I was asking.
Don't get confused with resistance and Ohm's law. Okay? Resistance is, can you tell me which one is Ohm's law? First one or second one? Or both are same? Which one is Ohm's?
First
Huh?
one, first one,
First,
first one.
First
first
one.
one.
First one.
First
Ohm's
one, sir.
This
First one.
this is the Ohm's law. Okay. This is not the Ohm's law. This is the definition of. So at any point of time, whatever might be the voltage and a corresponding current level will give you the resistance at that particular point. Okay. And here the resistance is considered to be constant. Now the resistance that I am talking of is the resistance of the path through which the current is flowing and it is getting dissipated. Okay. In resistance, the external resistance which you are going to connect, listen to it carefully. The external resistance that you are going to connect, we assume that this is fixed at 5 kilo ohm. Okay. But it is not so. Right. Because the value of, if it is 5 kilo ohm, it is quite okay. You can neglect the change in resistance level. But if it is in 5 ohm, then even if it is 5% change in resistance level, now you know why the resistance changes? Due to heating effect, resistance changes?
Yes, sir.
Yes.
Yes.
So when current is flowing, there will be a heat dissipation across the resistance and the resistance changes. This is first aspect, external resistor. Second is, whenever we are talking of the resistance inside the device, that means there is no external resistance as such connected except RC and RB and RE. But the path, whenever we have discussed this, whenever we have drawn the circuit and told that okay, IC is flowing, this IC itself is non-linear. Okay, this is not constant current. This IB or IE, whatever it is, even though we say that okay, it is 5 milliampere and so and so. Okay, but any PN junction characteristics you probably have come through the Shockley equation, Shockley diode equation, right? The current flowing through any junction is, and actually, you remember that equation or you have not studied that?
No, sir.
Yes, sir. That is I is equal to I naught e to the power nu v by
Yes. That
v
e to the
minus
power
1.
means it is nonlinear characteristics. Okay. The current characteristics itself is nonlinear. So if that current is multiplied with your so-called ohmic resistance, so the total potential drop itself is nonlinear. Okay, but for simplicity, we assume that okay, IC is 5 milliampere, RC is 4 ohm, and then multiply it in a very scalar multiplication and then get the result, which is not actually true. Because current generated or supplied to the circuit or from the circuit, all are ideally, all are nonlinear. Right? So there is no ohmic resistance, and that's what I told. None of the component will be considered, truly speaking, to be considered as ohmic contact. Any other queries? Any questions? Okay,
Sir,
thank you.
please share this note, sir, after the end of the class.
Sure.
Okay, sir. Thank you, sir.
Okay.
Thank you, sir.
Sir,
Attendance.
sir, please show first three slides, sir.
First,
First three slides. Thank you, sir.
You will not take the attendance.
it is already automatically it's recorded. You need not to bother about that. Okay,
So shall
this
we leave?
MS Team. The moment I switch off this session, automatically it will be downloaded in my folder. Okay. Manual attendance is not required. Automatically it will be counted, and you have to be present at that point of time whenever it gets switched off. Which one you are telling? First three.
Yes, sir.
This one.
Yes, sir. Yes, sir.
It will be available in your class note. Okay, don't worry.
Thank you, sir.